हाँ चला चला, एक्चुअली लिखने में सही रहता उसमें। चैट चैट, ये आ गया रिकॉर्डिंग। चलिए चल रहा है। ओके सो okay, so let's start with the uh, so maximum likelihood estimator of the normal distribution. And now I'm in this in this slide. I just want to recall what is normal distribution is, what is the expected value of normal distribution, what is the expected value of x square when this is normally distributed, and what is the variance here. So this is all of you know. I assume that you know all these things. So this is a form of a normal distribution, univariate normal distribution specifically. Univariate means that x is having only one component, and the mean is mu here. So if you draw it like this, so whatever the middle point is having a highest probability, that is mu here, and the variance is sigma square. So the other form of variance, you can write it equals to Ex. If you remember the last slide, last lecture slide of probability, we have expressed the variation of x in this form. So because Ex square is equals to this, Ex equals to this, and when you do Ex square minus, so this is mu square, it will cancel it out, and this is the sigma square here. So now what is this maximum likelihood estimate of the normal distribution? You just a small correction. This is this. So the maximum likelihood, I told you what in the last yesterday, what is IID? It's an independent identically distributed data. So let's let data set X is IID drawn from a normal distribution where true estimates are mu and sigma square. So let's assume that I had some normal data. This was the data which true mean is mu, and the true variance is sigma square. This is my true function, right? This is my true distribution. So I just find out some values here. So these are these values now. These are these values. I want to fit this. I want to find out what is the normal distribution using only these 4 data points. So there could be different forms of normal distribution. This could be this is there. So I want to find out which is the maximum likelihood maximal likely distribution is there. So we'll use the same technique what we did in the previous class, maximum likelihood. So now whatever the maximum likelihood estimation gives me, that I am representing by mu sigma square. So in this case, for an example, out of these two, this is the one and this is the second one. So for example, this is the most likely one. So whatever the mu and variance this is giving, that is that is my estimate of the maximum likelihood estimate of variance and square. So for an example, maximum likelihood function of the black points. I already showed this thing in a figure. For an example, these are the black points. So these are the black points, the maximum likelihood distribution. Just to for an example, I assume that most of them knew, but for most of them, that when we say that the points are Gaussianly distributed or normally distributed, and if this is a mu, it means, and this is the x, it means not this is what we draw. This is graphical representation, but actually it means that the points are, most of the points are available here. So the density of the point, availability of points is maximum here in this range near to mu, and it just gets scarce here. So when you showed this thing graphically, so it is nothing but like this. Sorry. So when you want to graphically show it, it is like this. So this is mu. So these are the black points. Let for example, these are the data points which you want to fit, So the maximum likelihood function that is drawn is this red one. So we get therefore write the probability of data in the form of likelihood function. So I told you that all those these x are IID, identically distributed. So now because these are identically distributed, so the probability of each x is this one because this is normally distributed, and the probability of a given x, let's say x1, where the parameter of normal distribution is mu and sigma square true. So this is the probability of my first x1. Is likewise the probability of my second point is it is x2. Now the maximum likelihood, now the likelihood function is because they are IID, I can multiply these. So this is a product of n points. I am multiplying it now. When just to recall that this is the normal function. So for an example, if you want to find out what is the value of x1 here, you just put the x1 here in this expression, and what because mu and the sigma, you know, if you know the parameters of this Gaussian distribution, by putting x1 you will find out what is the value of a Gaussian here. So these are very trivial things. I don't have to go it again and again. But I assume that you know the Gaussian distribution. If you don't know, you just go and read it because this is a minimum thing that you should at least this much you know for this course. So now this is the probability, and they are identically distributed. The likelihood function says that it is a product of that. So when when I multiply all these distributions, so it is nothing. If I can write this function, it is like the product of I equals to 1 to n, and this n is nothing but this expression. So it is product of 1 to pi sigma square half exponential minus 2 sigma square x minus mu square, this one. So this is this expression. Now we already discussed that if we want to find out the maximum likelihood function, we can take the log of it. This will not affect anything, but it will help us to make our analysis easy in terms of mathematics. So when we take the log of it, so if I take the log of this expression, so log will convert the product terms into the sigma term, right? So this product terms will go to the sigma, and sigma log of 1 to pi square half plus this exponential will get cancelled off the log, and it will come plus minus half sigma square x minus mu square, right? So when you do it, you will get this expression. So this is a log likelihood function. So this is a likelihood function. When you take the log of this one, this is the value of n. This is the value of n that I have written here. When you put this value of n, this is the product into this expression. When you take the log of it, you will get this expression, log likelihood function. So it is just a representation. So now you want to find out what are the parameters that maximize this expression. You want to find out what are the parameters that maximize this expression, that is a maximum likelihood. So this you want to differentiate it with this sigma square and mu, because these are the two parameters which you want to find. This is the maximum likelihood value you want to find. So this is the expression you want to differentiate it with the mu and set it to 0, find out the value. Then you again take this expression, take the derivative with respect to sigma square and set it to 0 and find the value. So if you do it, you will get it the that the estimated mu from the samples is nothing but the sum of all the samples 1 2 plus up to xn divided by just average. It's just average, simply an average. And the variance of this sample, right, maximum likelihood is for the sample. If you this is so the samples whatever you get for those samples, the maximum likelihood mu is the average of those samples, and the variance is a simple variance. So the from here you get the mu and you know how to find out the variance. So this is variance of a sample. So if you have x1, x2, x3 and somebody find you what, and somebody told that this is these samples are drawn from the Gaussian. Find out what is the maximum likelihood parameters of this Gaussian. So maximum likelihood parameter for this Gaussian are two parameters, that is sigma square variance and mu. So you will find mu by x1 plus x2 plus x3 divided by 3. So this is the mu maximum likelihood function. And this variance, how you will find out, this is mu, right? So now x1 minus mu ml square plus x2 minus mu ml square plus x3 minus mu ml square divided by whole expression divided by 3. So if you have given these 3 points, that's how you find out the mu, that's how you find out the mu, and that's how you find out the variance. So just to see, like for a simple case, for an example, if I want to differentiate it with the help of a mu with respect to mu, so let's say I write this function. Oh my god. So let's say I write this function with L, right? So differentiate of L with respect to mu, what I will get, this is constant minus half sigma square, and this term will be n equals to 1, and you know the derivative, by the derivative formula it is minus mu, by product rule it is minus 1. So right, this minus plus 2 will cancel this 2, and this is the derivative, you have to set it to equals to 0. This term will not consider because it doesn't have any mu, it goes to 0 in the in derivative. So you left with this expression 1 upon mu square sigma n equals to 1 from n n minus mu equals to 0, right? If you open this expression, this is 1 upon sigma square sigma n equals to 1 n x n minus, this is a constant, it is n mu, right, equals to 0, because this summation means you are adding this mu n times, so it is n mu. That's why I read this. And now it is this will go to this side, so this will go to this side. Now variation will go. So okay, sorry. So you can remove this. You can take this variation to this side, and it will get multiplied to 0. So it will also get away. It will also get away. So there was a mu expression, right? So I will take this mu square to this variation term to this right hand side, and it get multiplied to 0. So 0 will be 0 again. So this terms also get away. Now if I will open this term, So this term is nothing but sigma n equals to 1 to n mu x n equals to mu n, and this mu will be 1 by n. This n will go to this side. So it's a very simple thing. And likewise, if you do it for the for the maximum likelihood, you differentiate this function with the variance square. So this term will be the same, minus half to sigma n equals to 1 to n xn minus mu square. This term will get because this is, x minus 1 derivative is minus 1 x minus 2. So this variation, this sigma square which was here, it will get minus sigma square, and because of this minus, it will multiply by this minus and it will get plus, and here minus n by 2 log of x equals to 1 by x, so it will get 1 by sigma square, so it will get sigma square here, and this third term will get 0 because it don't have any sigma square. When you solve it, you will get the same expression. You will get the same expression 1 upon sigma n equals to 1 to n x n minus mu ml square. So the point is, you can use these sensors. So what I'm trying to say that if you have any Gaussian distribution, if you somebody say that you have some points x1 to xn, and somebody says that these are drawn from some normal distribution, find what is the maximum likelihood estimate of this of the parameters using these points. So you can find it by, you can find the mu of these by this expression, and you find the maximum likelihood of the variance by this expression. So you can see that whatever the mu you are finding by maximum likelihood estimation is actually the same mu. So what I'm trying to say in this slide, that whatever the mu you are trying you found using the sample data, that mu, the expected value of that mu is actually the true value of mu. So what exactly I mean to say, for an example, this is the data, this is the true Gaussian distribution, and let's say I have 2 points here, I drawn 2 points here, 2 points here, and 2 points here. So using these 2 points, this is the Gaussian distribution I formed. Using these 2 points, this is the Gaussian distribution I formed. Using these 2 points, this is the Gaussian distribution I formed. But when I take the expected value of all these three, so the mu will be the same here, and which is the same mu which was present in that original data. So mathematically, how can you say that the expected value of mu maximum likelihood is this? This is the formula of maximum likelihood, sum of x divided by n. Where, because this n is constant, you can bring out this constant from the expected value term, so this will go out, and this expected of xi equals to expected of value of x. Why? What I am saying here, that every term, because it is IID, the value of every x, expected value of every x is the xi. So now I'm multiplying with n into ex. This n will get cancelled out, and you find out that this remain with the expected value of x, and expected value of x is mu. So this is same. Now what we are saying, what is the expected value of maximum likelihood? So maximum likelihood expected value is this. When we are saying what was the expected value of mu, maximum likelihood of the mean, it was a true mean, right? So there that sample expected value is equal to the true mean. That is right. But when we say what is the expected value or the expected value of the variance likelihood, it is the sum factor into the true variance. So we can see from this expression here that the true variance is not the expected variance is not equals to the true variance. So this is how we proved it, that we use this maximum variance formula, we put it here, we expand this formula, this expression we got it, and because this is x bar, you come out, and this expression sigma of I equals to 1 to n xi equals to nx. So I put this, from this thing I put this thing, and likewise we solve this formula. Just a minor correction, that x bar I used on this slide is nothing but some mu, estimated mu of a sample, it is. So in short, what I'm trying to say, that if the expected variation of maximum likelihood is some product into the true variation, so I have to normalize it again. So what I can do, I can multiply it by the reverse cons factor, n by n minus 1. When I multiply by n minus 1, so I am multiplying my maximum likelihood function with n by n minus 1 just to normalize it. When I multiply by n minus 1, so this value is nothing but the true mean of the sample divided by n. So this n will get cancelled by this n, and you will left with this expression. So maximum likelihood estimation is biased in case of variance, but maximum likelihood estimation is not biased in case of mu. So this is important, you should remember it. Let's revisit the curve fitting problem now. So this was my curve. Now I am reformulating that problem what we have done before in terms of probability. So basic idea what we are trying to do here is that, let's say I have these points, and this is a line here. So we are making a Gaussian distribution for every point. Right? And what we are saying, that we want to maximize this probability. So in this case, that we can maximize this probability only when the line goes from this peak, and this peak. So this is the ideal case. But for an example, if this is the case, so then this is a normal distribution here, this is a normal distribution here, this is a normal distribution here. What is the line that can maximize this probability? So I have to go by this line like this, so that it will increase the maximum probability. So this product multiplied by this product multiplies this product should be the maximum one. So whatever the line satisfies this one, I will take that line. So how I will represent this? So this is the curve. For every point there is a distribution for that target value t, that is normal distribution. So this is x for which I am predicting. When I put this x into this expression, it will give the normal distribution where mean is the curve value. So mean is the curve value. So this is my likelihood function. Just to recall, that normal distribution was like this. X So normal distribution was like this: x mu sigma square, right? So this was my normal distribution. This was mu, this was variance. And I am just drawing the value of x and it give me a probability. Here in this case, rather than taking fixed mu, I am taking the mu whatever my hypothesis is giving. So let's say this is the hypothesis. For example, just to understand this, for an example, my hypothesis is a line. So it will be of form W0 plus W1 x. So this is the form of line. Now this is the mean. So every time I take the line, let's say this is the line, I take the value of x. I put this value of x and it gives me the value on line. So this value of line will be considered as a mean now. Now I draw a Gaussian distribution because this is a mean here. This will be a probability. If I take this value x here, this is the value on line. Now this is the new mean here. I will make the Gaussian distribution. This is my new Gaussian distribution. If this is the x, I will put this x into this hypothesis. It will give me some value on line. So this value of line is this. This will be my new mean. I will make the Gaussian distribution. Oh my God. So this is my okay. I think for example this is x. So this is my mu x. So it will be a mean here. So I will draw the Gaussian distribution using this mean now. So this value here is given by the hypothesis whatever I am taking. If this hypothesis is a curve, let's say this is a quadratic curve. If I take the value x, this, so this quadratic curve give me this value. This value. Now this is the new mean. I will put the Gaussian distribution here, right? So I hope you understand what this expression is saying. So this is the hypothesis. In this hypothesis, I am putting some value. That value will be my new mean, and this is the variance. So this beta 1 upon beta equals to sigma square. It's just another representation. Sometimes we say this precision. So don't be very confused. Every time you see my beta minus 1, it is nothing but the sigma square, right? So the likelihood function of the Gaussian distribution was this. In our previous slides, we have seen that, right? So this was the likelihood function of the Gaussian distribution. This is same. Now, rather than this mean, I have put this mean, this hypothesis mean. And this value is same here. Because the order doesn't matter here because this is a square. So everything remains the same. This beta, this sigma square replaced by 1 upon beta. So 1 upon beta, because this is a negative sign here, it becomes a positive sign when you bring this beta up, right? So this is same. This likelihood function is same. The only difference is that I replaced variance with 1 upon beta and this mu with this my hypothesis y, x, and w. Now I want to maximize it. Now when I want to maximize it, I will take the derivative with respect to W. When I take the value with respect to W, this is constant, it goes away. This is constant, this goes away. This is just a scaling factor, it goes away. What do you mean by it goes away? It means that whatever the value W will give, will maximize this expression, that same value will also maximize this whole expression. That these terms will not affect that value W, because W does not depend on these values. So if I want to find out what value of W will maximize this whole expression, I can just concentrate on this expression only. I just ignore these two terms, I ignore this beta, and I will focus on the remaining one. If I will see it separately, what is this? This is the error function. This is the error function. So what we can say, the sum of square errors, the sum of square error function has arisen a consequence of maximum likelihood under the assumption of Gaussian noise distribution. So it is same what we have done in the last class, right? I just shown that if you take the sum of square error function, it is nothing but the maximum likelihood function. That's why I have taken that previous class yesterday on Saturday. That class is because that will give you a clear picture of what I am doing here. That was a very simple case, and now I'm using a Gaussian and curve fitting problem. So now this sum of square error is nothing but the maximum likelihood function. It is important under the assumption of Gaussian noise distribution. The noise that I assumed is a Gaussian noise. So if I take this, if I take the maximum likelihood with the variance, this is the same expression. What is the sample variance here? By using this derivative and all, you can do it. So this is the distribution of over T in contrast to point estimate, which we have done previously. So what this point is saying, for an example, if you haven't considered this normal distribution thing, so if you have taken some function, then when you every time you take the value of x, it will give you a specific value of y or t, specific value of this axis. But when you now, because you are considering the normal distribution, it gives you a probability rather than a specific term. So you want to maximize this probability for that particular x. So whatever x you take, you want to return that t that is having the maximum probability. So this is the difference there. Now let us take a step towards a more Bayesian approach. Let's take some questions first. Okay, I will take some 5-6 minutes questions. I don't want you to be very much confused. What do you mean by normally distributed? It is not clearly distributed. Normal distributed, you should know what is normal distribution. Normally distributed means that the data is distributed by the parameters mu and sigma. For this, sir, you have to see what is normal distribution. Then you will not ask this question. You should revise this thing. What is sigma? Sigma is a variance. A small point. Log is in which case? Yeah, sorry, I didn't mention. Log is it's a natural log. But that's why it is cancelling this exponent term. So the base of the log is e. Which book to follow this topic? I am teaching this topic. This whole slides is from Christopher Bishop, chapter 1. So just to read the chapter, you must go through this slides. Then only you will understand what the chapter is. So for your simplicity, I'm taking this lecture from chapter 1. Otherwise, I have to take this chapter from chapter 3 also. But once you go through this slide and chapter 1, then only I will take, because that will be too heavy for you, what I feel. That's why, for your sake, I am considering this lecture first before going into the depth of the third chapter. What is n? What is n? Which n you are talking about? One. This is normally distribution. This is a symbol of a normal distribution. Sir, you can refer some book to revise probability statistics. I shouldn't say that which book you should read or something, but I feel that chapter 2 is enough of Christopher Bishop. Chapter 2 is enough for this probability. Can you please explain how for every point distribution curve is fitted? So did you attend my yesterday class, Brani, Barani? I don't know. Okay, so there's the same class which I told how to come up with expression in maximum likelihood. That's what the same thing I am doing here. The only thing that is changed here is that that was a probability, that was a Bernoulli distribution there, and now it's a Gaussian distribution. That is the only change here. Okay. Okay, fine. So now let us take a step towards a more Bayesian approach. So an introduction and introduce a prior distribution. So so far we haven't considered an in Bayesian approach, as we yesterday did, that we have to take that prior knowledge, right? So let's take some prior knowledge here also. The prior distribution. Yesterday, if you remember, we did that prior distribution. We used beta distribution for that prior, right? So here we again used prior distribution, but rather than beta distribution, we will use the normal distribution again. So we will use normal distribution for the prior. The normal distribution is of this form. This alpha is again 1 upon alpha is equals to variance of this. Let's say the variance. This is the variance. So likewise, in the previous question, one beta was the variance 1 square. So this is variance 2 square. This 1 upon alpha. So there are two different Gaussians. One Gaussian variation is sigma 1 square, and other Gaussian variance is sigma 2 square. So here 1 upon alpha is the precision factor of this prior distribution. This what it is saying, that we are drawing the, because this is W is a vector, so this is a multivariate Gaussian. For an example, if W would be of 2 dimension, then this Gaussian will be a mountain, and the peak is on this origin, let's say. So these curves that I'm showing here is a cross section of this. So in 2 dimension, if you want to show the Gaussian distribution, where each coordinate is not correlated to other coordinate, means to say that the covariance matrix is only diagonal, having only diagonal values, and other are 0. So this is alpha, 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 right, and all are same. So this will be a mountain here. And for an example, if this would be alpha 1 and alpha 2, and these alpha 1 equals to alpha 2 would not be equal, then the Gaussian distribution would be either like this form or this form. It depends upon whether alpha 1 is greater than alpha 2. But if alpha 1 is is equal to alpha 2, then it is totally round in shape. And the tip of this mountain depends upon where the mu is. So here mu is 0. So this prior is defined by the Gaussian distribution, multivariate Gaussian distribution, where the mean is at 0 and any of the coordinate is not depend on other, not correlated. That's why it is saying that this is the identity matrix. So if you multiply this alpha minus 1 with identity matrix, what you will get 1 upon alpha, 1 upon alpha, 1 upon alpha. If there is a d dimension, it will be go 1 upon alpha up to the d dimension, and all these all other values are 0 in it. So in 2 dimension, if I would say that then these equal to this, so there will be, it will be totally round Gaussian. So this is a multivariate thing, right? So okay, okay, okay. Fine. So this is how generally you write multivariate Gaussian distribution. Okay. So this was just value what we have taken from here, right? This is this value. This is this value. Likelihood function. That is the product of every data variable or sample, sorry. And this is the product of a prior. I am multiplying it. If I will multiply it, the most probable value of W given the data is maximized value of W in posterior distribution. So I am just finding out that value of W in the in short, if you recall the last lecture, yesterday lecture, I am trying to find that value which maximize this expression, only this expression, right? So so in short, if you simplify it, you find the maximum posterior is given by the minimum of this value. How? So just leave this statement for a while. And what I'm saying, I have to maximize this expression. I want to find that value which maximize this expression. So I want to maximize this expression. I want to find out what is the value W that will maximize it. So this is this expression, right? And this prior W2 is this expression. I take the log of this. I have already taken the log of this. When I take the log of this, so when I take the log of this, it is nothing but ln alpha upon 2 pi m plus 1 divided by 2 plus log will cancel with this exponent, and what will come? Minus alpha upon 2 wt w. This is the expression what I get. So this will get minus, this will get cross, so this minus will be the minus, right? Okay, just a minute, just a minute. So this minus remains. So what will left out is this expression. This expression. What was that? I think minus. Yeah. So this is that expression. So this expression multiplying, I'm multiplying this expression with this expression. When I take the log of this plus log of this, it will get added. So this will get added, right? So this thing, what is there, plus this thing. Now I will take the negative of this whole expression. So just a minute. So sir, if I will write this thing, so this whole expression will be like this: minus b by 2 sigma n equals to 1 n y x n comma w minus t n square plus n by 2 log n beta minus n by 2 log n 2 pi plus ln alpha by 2 pi m plus 1 divided by 2 minus alpha by 2 wtw. This is the whole expression that I got. Now I want to maximize this expression. So if I want to maximize this expression, if I take the negative of it, it is the same as if I will take the minimum of that expression. So I will take the negative of this. So the negative will convert to this, will convert to minus, this is convert to plus, this is convert to minus, this is convert to plus. So this will be the negative of the expression. At first I have to take the maximum value. Now because I have taken the negative of this function, I have to take the minimum of it. It is same. So this expression, what is that value of w that will minimize this expression? Now to minimize this whole expression, because this term is negative and is constant, I cannot do anything with this. This term is also negative and is constant, I cannot do anything with it. This is also constant in terms of w, I cannot do anything. The only thing with left is this b by 2 sigma n equals to 1 n y x n comma w minus t n square plus alpha by 2 w t w. If I will minimize this value, the value that will give me that value that minimize this expression will definitely minimize this expression, and the value that minimize this expression will maximize the positive of it. So ultimately what I am saying, eventually this is the expression that I has to minimize. And if I want to write this w is nothing but it's a norm of square, and this you can take, this is b, right? So here lambda equals to lambda alpha by beta. So this is same what we have done, what we used in regularization. So Bayesian approach, when you take the prior of it, will result in the same expression what you did in the regularization. So for the I can understand that most of you could not understand because of the basics, and it really need a lot of attention and concentration. So please go through this chapter 1 first, as number of times as you can. Go to the basics, understand it thoroughly, and after you have a genuine questions, you can post me and mail me. I will reply and try to address this question. After this chapter 1, you have to go to chapter 3 and you read only section 3.1. So I'm for now I haven't gone into the detail of chapter 3 because I feel that most of you have to go through chapter 1 thoroughly first, then we will understand this chapter 3. So my request to all of you who are really interested, just go and read chapter 1 of Christopher Bishop and try to find out what is there. Please send pre-request. Okay. Pre-request I already told in the first chapter, but see, it's not a one-day game. To be very true or honest, it For the concepts, you should go through. If I directly say just read the chapter 2 of Christopher Bishop, then also most of you don't understand the chapter 2 as well. So depend upon your like mental level, or depend upon your comfort or your understanding. You have to choose that exact material. It differ from everyone, from each one to one person. So find accordingly the material, whatever you understand, and go through it, and then read the chapter 1 of Christopher Bishop. Then after that, I will, in the next week, I will going to take this chapter 3 of Christopher Bishop. So shared with us while choosing the course, so may little irritating to see lack of knowledge that you are considering as per requested to this course. Sorry, I will read it again. Frankly speaking, the course prerequisites were visible to us on day 1 of the contact hours, and it wasn't shared with us while choosing the course. So you may find it little irritating to see a lack of knowledge that you are considering as prerequisite to this course. What should I say? Every week I will have 4 hours of class. Can you tell any reference to start from the receipt? So what I can say that you have to read it, read a lot. Then you can understand it, and you should. Then you can appreciate it. Understand it, but I don't. I am not appreciate. I don't appreciate it. So you will appreciate it only when you really understand what I'm talking about and what I'm teaching. And frankly, if I go according to, like, if I really want to teach, then I cannot cover the whole course. That is also a big problem with me. If I can because if I will go very slowly and to your pace, or but according to the so that each one can understand, I really doubt that I can finish this course within a given time. Okay, fine. So next class also, for just one simple small tip, that you must understand what are distributions, what is Gaussian distribution, what is Dirichlet distribution, what is beta distribution, what is probability, expectation, variance. You should have a very clear idea about it. Then you can really appreciate the content of this course. Okay, fine. Thank you, sir and madam. Okay, okay. Hmm.